Hi, I'd like to do another formula with you for decay rate, but this time it's an integrated formula. So we're going to have a natural log inside of it. So here it is, the integrated formula. Natural log of A over A naught equals negative KT. Now labeling everything, A is your amount remaining, A naught is your initial amount, K is going to be your rate constant, and time elapsed, that's going to be your T. If you have questions on rate constant, go to the rate playlist and you can watch the videos on the rate constant, first order and second order reactions. This is actually going to be our rate law from the, or integrated rate from first order reactions, half-life for first order reaction is going to be half-life equals 0.693 over K. And again, that T sub 1/2, that's my symbol for half-life. Some of you might know this from math, that the natural log of 2 is 0.693, and then K is going to be the rate constant. If you're in AP chemistry, these will both be given to you, except this, they've separated. You'll remember with natural logs, when you have a quotient, to separate the quotient, it looks like this. You subtract the denominator. So it'd be natural log of A minus natural log of A naught equals negative KT. And it's from this that we get the graph. You can also watch from rate laws the graphs for first order, second order reactions. Now, we're doing nuclear chemistry. And in nuclear chemistry, everything is first order, okay? Every reaction, every decay rate is going to be first order. So we're going to use this formula and this formula, half-life, and then this formula, integrated formula, to find the decay rate. So first order, we use this for nuclear chemistry. Another interesting point, this quotient right here, the amount remaining divided by the initial amount, when you divide that, that always gives you the percentage of the amount remaining. Always gives you the amount remaining. Let me give you an example. Let's say that I start with 25 grams and the amount remaining is 5 grams. If I divide that, I have 20% remaining. So it'd be 0.2 remaining. That's going to be significant because there's a good chance you're going to see problems that will say 10% of the initial amount is remaining. They don't give you the initial amount or the final amount, they just give you the percent remaining. Well, you can plug it right there. Now be careful, because sometimes they'll say 70% was consumed. Well, you can't put 70% here, you have to put the amount remaining. If 70% is consumed, how much remains? 30%. So you put the 0.3 right here. So common way that questions can be asked, just want to give you that little tidbit. And then again, you might see in your textbook this integrated formula written out where the quotient is separated just using our log rules. Okay, now I've come up with 4 problems that I'd like to do with you to help you practice using this integrated formula. Here's the first question. We are going to have an amount remaining of 3.8 times 10 to the 3 disintegrations per minute. So that's the amount remaining, okay? Our initial amount that we began with was 3.35 times 10 to the 3 disintegrations per minute. And we were told that we have 2 days, that we're going to have 2 days that this is going to disintegrate, or that it disintegrated. So that would be my T, how much time we had to disintegrate. And what it wants to know is, what is the half-life? What is the half-life? Well, we're going to have to use both of these formulas. If I want to find half-life, I have to know the rate constant, and I'll have to use this formula to find the rate constant. So let's go ahead and plug in what we have into our decay rate, right here, this integrated formula. We're going to have the natural log of the amount remaining, 3.18 times 10 to the 3 disintegrations per minute. So this amount remaining, that's just going to be a nuclear unit, so don't worry about that if you're not using that. It's just a unit that we use in nuclear chemistry. The initial amount was 3.35 times 10 to the 3 disintegrations per minute equals negative K. That's what I'm looking for. And the time elapsed was 2 days, 2D right there. So when I put this in my calculator, and be really careful, you have to put the quotient in your calculator. So I do natural log parenthesis 3.18 times 10 to the 3 divided by 3.35 times 10 to the 3, and parenthesis. Here's the mistake that students make. They'll do natural log of 3.183 times 10 to the 3 divided by natural log of 3.35 times 10 to the minus 3. That mathematically is not correct. You have to do this number divided. So you could even divide it and then take the natural log of that number divided. And when you do that, you will get, so I did this where I actually divided it to drive this home. Divided those two numbers and I got the natural log of 0.949 equals negative k 2d. So take the natural log of that 0.949 and it gives us a negative 0.052 equals the rate constant times 2d. Now watch the units on this. I'm going to divide both sides by 2d. Because remember up here, those the disintegrations per minute, they canceled. So I'm going to divide this and we are going to come up with k, oh, and that was the negative, so sorry. K is going to equal 0.026, and wait for it, the unit per d. The rate constant, the unit for the rate constant for a first order reaction is always per time, is always per unit of time. And again, go to my rate playlist and you can watch the videos on the rate constant. Honestly, the point of the rate constant is to adjust units. So that's really, really significant that it's going to be a number per time. And here the time is days. So now I can come back to this formula. Okay, I found K, my rate constant. Now I can plug it in over here to find half-life. So let's go ahead and do that. I'll erase this. We'll plug that in. So we will have half-life equals 0.693 divided by 0.026 per day. Fraction divided by fraction, that day is going to come to the numerator. When we divide that, the half-life is 26.6 days. And there's our answer. Okay, nice. So there's one problem for us. I want to do a couple more just so you get really comfortable. I tried to pick some problems that are set up a little differently, just so that when you do your homework, if you come to something like, I haven't seen this, hopefully I've covered one of these for you. Okay, so in our next problem, we are going to have a half-life of 200 years, okay? 200 years. We're going to have an initial amount of 6.5 times 10 to the 12. We're going to do disintegrations per minute again, and the remaining amount is 3 times 10 to the 3 disintegrations per minute. And we want to know what's the time that's elapsed. How long did it take to go from, wow, a lot, 6.5 times 10 to the 12, all the way down to 3 times 10 to the 3. How long did that take? So they gave us half-life. Now, to find time elapsed, I've got amount remaining, I have amount initial, I don't have K. We're going to have to use our half-life to find K. So let's go ahead and plug into this formula right here. Our half-life, 200 years, equals 0.693 times K. So I'm going to multiply both sides by K, and then I'll take my K times 200 years, and let's divide both sides by that 200 years. So 200 years, and K is going to equal 0.003465 years. Okay, so we found our K value. Now I can take initial amount remaining, and our rate constant, plug it up here, and we can solve for T. So let's go ahead and do that. I'll erase this, and we'll plug in. So it will be natural log of the amount remaining, and I'm going to put this whole thing in a quotient. Remember, we have to do natural log of this quotient, dividing that. 3 times 10 to the 3 disintegrations per minute divided by 6.5 times 10 to the 12 disintegrations per minute equals negative K. We found that 0.003465 years times the amount of time it took for it to decay a lot. Okay, so putting this into our calculator, if we take the natural log of, let's see here, actually I just put this all together in my calculator. So I did natural log of this quotient, and then I divided by negative 0.003465. Notice this unit right there is going to cancel. And we will end with, when I divide this over, our amount of time is going to end up being the years. That's what we'll be left with, is the years. So if I do the quotient, take natural log, divide over the negative 0.003465, the time that it took, wow, 6,204 years. A long time. Took quite a while for that to disintegrate. Okay, two more that I'd like to do with you. This next one is when they tell you you have an amount remaining. So in this example, we're going to say that we have 10% remaining. Now, another way that they could give this to you is they could say 90% was consumed. They could say 90% of the samples consumed. So you think, well, what's left over? Because this quotient is always amount remaining. So if they consume 90%, you're like, oh, that means I have 10% left over. So they're telling us that we have 10% remaining. Well, 10%, you could use any numbers to come up with 10%. You could do 10 divided by 100 gives you 10%, 0.1. Here's how I write it. The remaining is actually going to be A divided by A naught. That's the amount remaining. That equals 0.10. That's my 10% that's remaining. So that quotient, the total quotient, equals 0.10. In addition to that, they tell us that it took, the time elapsed was 37.6 years, and it wants to know what's the half-life. What's the half-life? So in this, it almost feels like there's not enough information, but remember that 10% gives you the ratio of both the A and the A naught, the initial amount compared to the amount remaining. So to find half-life, I have to have K. We're going to have to use this formula here to determine K. Let's go ahead and plug this in. The natural log of that entire quotient, which I know is 0.1, 10% remaining, equals negative K, my unknown, times 37.6 years. Okay, let's see here. So if we take the natural log of 0.1, divide this over the 37.6 years, we are going to get K equals 0.0612 years. Per year, because when you divide that over, the year will be in the denominator. So it's going to be per year. Now I can just plug it into my half-life formula. The half-life is going to equal 0.693 divided by 0.0612 per year. Fraction divided by fraction, the year will come on top in the numerator, and our answer, half-life, will be 11.3 years. 11.3 years. And so even looking, let's see here, 11.3 years. So if it's 11 years, it looks like we've undergone a little more than 3 half-lives. So if I divided this in half, we were going to, so divide 37 years in half, puts you, what, at about 16 and a half years. We'd have 50% remaining. Divide that in half puts us at about, what, 8 years. We'd have 25% remaining. Divide that in half again. Let's see here, 16, 8. Trying to make sure that this makes sense for us, that the half-life would be, we'd have to go, so divide it in half again. So sorry, I was dividing the half-life, or the these years in half. I'm so sorry. I'm dividing, one half-life is 11 years. Okay, don't be confused. Do this with me again. If we divide in half once, we go 11 years, and that would be 50% remaining. Divide it in half again, we would be at 22.6 years. Okay, at 22.6 years, we're now at 25%. Divide it in half again, I'm at 12.5%, and I'm now at 33.9 years. And so if we divided it in half again, that would give us 6% remaining, but we had 10%, and it didn't go all the way up to, let's see, 4 half-lives would be 44. We're in between 33 years and 44 years. So we're in between 3 half-lives, 4 half-lives, yep, in between 12.5% and 6.25%. So that it all fits. If you go back and ask yourself, is this logical? Is it reasonable? And you had to watch me figure that out too. And sometimes you do, it's like, wow, that didn't make sense. Like, oh, I was thinking about it wrong. So good example of saying, is this reasonable? Does it make sense? Don't just do the numbers to do the numbers. Make it make sense. Make it make sense. Okay, so half-life, 11 years, and we went through the half-life a little more than 3 times. 3 half-lives plus some. Okay, one more problem. And I want to give you, and I wanted to do this one because the unknown is inside of the natural log. This is a reminder how to use the e function, e to the x. Just make sure that you're okay with your math on doing this. So here we have it. We want to know the amount remaining, okay? We want to know A. What is the amount remaining? Our initial amount, let's say, is 92 milligrams of a radioactive substance. Let's say that our half-life is 5,000 years. 5,000 years. So from here, we want to find the amount remaining, and that's all we're given. Well, if I want to find this A, I have to have, oh, sorry, there was one more piece of information, and that was the time elapsed. And we're going to say, here it is. The time elapsed is 15,760 years. Wow, a long time, 15,000 years. So I've got my time elapsed. I'm looking for amount remaining. I have the initial amount. We've got to find K. And the way we'll do that is again with the half-life. So let's use our half-life. We've got 5,000 years equals 0.693 divided by K. So I'll multiply both sides by K and then divide 0.693 by 5,000. And when we do that, our K value is 1.386 times 10 to the minus 4. And you're thinking, what's the unit on that? When I divide the 5,000 over, it'll be per year, per year. Okay, so now we can plug in to our integrated formula. We've got natural log of, here's my unknown. How much is remaining? A naught. The initial amount was 92 milligrams equals negative K, 1.386 times 10 to the minus 4, notice per year. And then when I multiply this, I have to be really careful. I have the same unit. This is also, right there, that's also year, time elapsed. So that's going to be the 15,760 years. Notice year in the denominator, year in the numerator. Year is going to cancel. Okay, nice. So I have an issue. That A is inside of the natural log. How do I get rid of that? We have to raise both sides to the power of E. So it's going to be E, and that becomes the exponent. E, that becomes the exponent. You remember, E raised to the natural log cancels out. I'm going to erase this so I can rewrite it over here. And that is going to give us A over 92 milligrams. So it unlocked that natural log so we could have access to that A. Now this, that actually becomes the entire exponent, negative 1.386 times 10 to the minus 4 times that 15,760. Wow. So putting this into the calculator, let's see here what I got. So I multiplied these, raised E to that number, and I got 0.11255. So check me on that. You can put that in your calculator. So I multiplied that negative 1.386 times 10 to the minus 4 times 15,760, did the E, and it's on your calculator. It's just the E to the X. Let me show you in case you need a little review on this. Okay, so there's natural log right above it. So I do my second and then do the ln, and that will give you E to the X. In fact, let me show you really quick. Let me clear all of this. If you go second, the natural log, you can see that little E raised to the power of X. And then I do parentheses, put in these two numbers right there, multiply that. And then you get the 0.11255. Okay, so now we're going to have A divided by 92 milligrams. And remember the years, those canceled out. So we're going to be left with, when I do 0.11255 times 92, we'll be left with milligrams. The amount of substance, the mass that's left over. And when we multiply that, the amount remaining is going to be 10.35 milligrams. 10.35 milligrams. Okay, nice. Now, I want you to think about this. Let's ask ourselves, is this reasonable? Always so good to check yourself this way. So our half-life is 5,000 years, and we went, what, 15,000 years? Yeah, right here. So we went actually a little bit more than 3 half-lives. So let's take our 92 and we're going to divide it in half, a little more than 3 times, okay? We're just checking to make sure this is reasonable. So 92 divided in half is going to be 46. There's 1 half-life. Divided, and that would be 5,000 years. Divide it in half again, we're at 10,000 years. And that would give us, what, 23? Now divide it in half again, that's 15 years, and that would give us 11.5. And then divide it just a little bit more. It would take a little bit more. We're moving into that 4th half-life, so yeah, that would be reasonable. That exactly 3 half-lives would be 11.5, and we're a little bit low, below that, 10.35. So reasonable means that we did it right. Okay, so 4 examples. Hopefully that helped you with decay rate using a first order integrated rate law. Have a good day and good work. Thank you.